Well, hi, everyone. Welcome to Tech Talk today, or for this month. We are going to look at a couple of technology updates over the next 45 or 50 minutes or so. As we go, we're going to talk about two different Wi-Fi technologies, or 802.11 technologies, actually. So we're going to talk about 802.11ax. These are evolutionary and kind of revolutionary, I think. And we're also going to look at 802.11ay, or otherwise known as Terragraph, and if you're familiar with this. And we'll get into the details here as we're moving along. But first, let's have a look at 802.11ax and kind of a little bit of a Wi-Fi review in general. What is it and why do we have it? Let's just go back and review this then. So 802.11ax is designed for these are four of the principles that it's designed. It's designed to improve compared to 802.11ac and any of the Wi-Fi protocols that have come before this. So AX, it's designed to serve many more Wi-Fi clients per AP than before. So we have mechanisms here. We're going to talk about a few of them that give us that ability to increase the density of clients connected to a particular AP. I had mentioned that here even in residential markets today, we have many devices in our houses that are talking on our Wi-Fi that we never had before. Our door locks, for example, our security cameras, our window sensors. If we've got other security devices within our house, we've got people's refrigerators can be Wi-Fi enabled. We saw washers and dryers that are Wi-Fi enabled. We've seen all sorts of different devices now that we have. And of course, everybody in a household today, almost right from young kids, all the way up, have smartphones oftentimes, and so there might be 3 or 4 or 5 smartphones in a house. There might be all kinds of stuff. When everybody's together, all of these devices need to coexist on Wi-Fi at the same time. When we move into the commercial world and we're doing Wi-Fi for an office or that kind of thing, of course we have the same issue, but on steroids. We have many devices, hundreds of devices that need to speak over that Wi-Fi. So 802.11ax is designed to increase the number of devices that can be served from an access point. We have density today, required density so we have, whoops, let me go there. There we go. We've got optimal, we need to have this optimal performance in dense environments. So again, it's not 1 or 2 Wi-Fi clients that may be associated to an access point. It may be 100 or a few hundred. One of the drawbacks of the contention-based protocol, the pure contention-based protocol, is that any device that has something to transmit just simply waits for clear air and then does its transmitting. So in 802.11ax now, we have a mechanism that is going to enable uplink resource scheduling. This like in access networks, when a subscriber module has something to say, it will say it in the uplink interval, and the access point will speak to the CPE devices or subscriber modules, whatever you want to call them, in the downlink interval of TDD. A TDD protocol, time division duplex protocol. So we're going to move. 802.11ax is going to take us towards the point where we can more efficiently schedule the air by actually having the Wi-Fi clients issue a bandwidth request. The access point will then schedule that communication. So now we no longer have to worry about contention. So we don't have to have the pseudo-random backoffs and other things that are part of the contention-based mechanism. We can take and again, have towards the end of having more Wi-Fi clients connected to an access point. And because of this scheduling business, we now can provide different types we can serve different types of Ethernet traffic over the link, whether it's SCADA sensor traffic, which are typically very small frames, and sometimes very many of them, to regular surfing traffic, which is typically low bandwidth required in the uplink, and then when the website answers or the movie streams or whatever it is, it occupies a considerable amount of bandwidth. We can mix these types together now because of this scheduling business, and accomplish that goal. So what's different with pre-802.11ax Wi-Fi protocols to what 802.11ax offers? So first of all, 802.11ac is OFDM. What does that mean? That means that the channel, the 20, 40, 80 megahertz channel, whatever it is that you've got configured in your access point, has that channel broken up into subcarriers, and these subcarriers are then assigned to each Wi-Fi client that requests bandwidth or that has something to say. And so the entire channel is used up for a certain number of microseconds with the conversation with whatever the frame is that's either going in the downlink or in the uplink from or to the Wi-Fi client device. In 802.11ax now, we're going to use OFDM-A. The A indicates here that we're going to take and divide up the channel in both time and spectrum. So now in 802.11ax, I can have more than one subscriber device be communicated with during the frame, because I can break my frame up now into smaller segments. So depending on what the traffic load is, OFDM-A can increase the efficiency a huge amount as compared to OFDM. In OFDM, if I have a small frame, I'm still using the entire channel, all of the subcarriers in that channel, and some of them might be filled up with no data. And in OFDM-A, those no data moments in the spectrum can be filled up with traffic to another subscriber module or another Wi-Fi client. In 802.11ac, base performance is single in, single out antennas right here, SISO. In downlink, there is an ability to use MU-MIMO, so that means we can talk to individual Wi-Fi clients together at the same time using different streams, Wi-Fi streams. But because it's OFDM, then the entire stream is dedicated to the communication with that one client. So I can have 2 or 3 clients in 802.11ac, depending on how many MIMO modes, the multi-user MIMO modes that I have. And so I increase my capacity 2 times maybe, or thereabouts with the MU-MIMO. But in 802.11ax now, I have both the downlink and the uplink scheduled. I have MU-MIMO operating in both the downlink and the uplink. And so I can take and increase the efficiency over the air a number of times because of the fact that I can use part of the channel, and I can schedule multiple groups of Wi-Fi clients to when there's a large volume of data to be passed over the air. It's just that much more efficient. 802.11ax or AC and before is a contention protocol only, as I mentioned. In AX, the AP schedules the over-the-air transfers. I can use up to an 80 megahertz channel in the specifications for pre 802.11ax. AX allows me to go up to 160 meg channels, and the specification, of course, could be extended to go even farther than that. When the link quality is very, very good, In AC, I can go up to 256 QAM as my modulation level. The specification in AX goes up to 1024 QAM. Typical operation for both are the same because it's the signal to noise ratio that we typically operate at in a Wi-Fi environment isn't that much different. So when we see a spec like this, up to 256 QAM or up to 1024 QAM for the operation, just keep in the back of our mind here that that in typical operation in both networks here, we are going to be operating kind of in the same range that we always did before, because our signal quality hasn't improved a lot. The Wi-Fi client is still a Wi-Fi client. It still has, your laptop still has, the small patch type of antennas inside, and your phone the same thing. So that's not any different. But what is different here is the fact that in order for me to get the higher data rates with 802.11ac and previous protocols, I had to take and shorten up the symbol time over the air. So I had to increase the data symbol length, or increase the data symbol, the number of data symbols per second in order to achieve the higher data rates. And I'm going to say that again. Here in 802.11ax now, for those of you who have taken an LTE course from any of the manufacturers, or if I've taught you, you know that that OFDMA allows for a longer OFDM symbol, which means that I can have more consistent non-line of sight performance and achieve the data rate that I need to. While I'm dealing with the walls, in this case of Wi-Fi, I'm dealing with walls and other obstacles, maybe trees outdoors, that kind of thing, in a much more efficient way than I could before. In the past, if you were, let's say you were planning a Wi-Fi network in a campground, for example, the idea of placing the Wi-Fi access point outside of your target campers or whatever it is, and then reaching into them was kind of a tough deal, because your range was so short because of the fact that this short symbol length meant that I've got to take and have really high quality signal in order to take and actually pass any traffic whatsoever. So now with 802.11ax, I'm relieved a little bit from that requirement, in that I have a longer symbol time, and so I have more consistent non-line of sight performance. We had a number of different standards before that were involved in pre-802.11ax. So here we have, just for example, 11n standard had a 2.4 and a 5 gigahertz, 2.4 standard, I should say, 5 gigahertz only for 11ac. So here I'm mixing. For if I have a 2.4 client, I'm mixing 802.11n and 802.11ac and the 5 gigahertz only. And so there was the protocol was complicated depending on who was the target of your communications. And client communication is grouping by time only. So therefore, I'm using the whole channel all the time in order to take and speak to a particular device. Here, as I mentioned, because of the 802 of the OFDMA, I can group by time and by subcarriers. All right. So here's the mechanism. 802.11ax uses a resource unit structure. They don't call them resource blocks like in LTE. So it's LTE-like, but it's not exactly the same. It uses a resource unit structure. So depending on what the device that needs to transmit has to say, and the traffic that's on the access point, the access point has the ability to take and use a large group of resource units, or smaller, or even smaller yet, or even very small in the case of when there's just bandwidth requests and acknowledgements that are going across the air. So we have in the smallest resource units, we have as low as 13 symbols. The next step up is 20 symbols, 52, 106, and 242 symbols at a time. And then this is taken and divided up over between subcarriers and the number of microseconds that it takes to generate this number of symbols. So we have this whole business of being able to calculate the capacity in much the same way that we do with a LTE or any other OFDM access type of network. And so here in the table here in the middle of the slide, I have the number of subcarriers, resource units, I should say, that we have involved in any of the channel widths, and the number of clients that can be simultaneously spoken to at the same time with this matrix of possibilities that the access point is able to schedule. At any given time on a network, we have all of these conditions happening at the same time. So it's possible that we have let's say that we're using a 40 megahertz channel here, for example. It's right here. So I can speak to a single client or a couple or 4 or 8 clients, or I can any combination of these that the scheduler can come up with in order to pass the amount of traffic that it needs to. This is a huge increase in efficiency compared to dedicating, one symbol of every subcarrier in the channel that 802.11ac does in order to take and operate. But the beauty of this is that with all this mechanism here controlling the physical layer, I still can maintain backwards compatibility with my access point. I want to bring out this point, that this mechanism allows me to dedicate all of my subcarriers, in this case right here, to an 802.11ac client if I need to. If I have an AC client that joins the 802.11ax access point, I can still operate in the old AC mode. At the same time, I can speak in AC, if I want to call that a language in itself, into 802.11ac clients that I have on the network. Efficiency gains, though, with the 802.11ax are lost when using 802.11n or AC clients that are mixed with AX clients. This is absolutely true today. So when we upgrade from let's say we've got 802.11n access points scattered throughout our organization, and I want to upgrade to AC, I may not see an order of magnitude increase in efficiency just by simply changing out the access point, because I haven't done anything with the clients yet. But as time goes along here, laptops and smartphones, for example, my Samsung S10 has an 802.11ax client in it. A Wi-Fi 6 client is in it already. So I can take and speak AX or Wi-Fi 6, whatever the brand of it is called, and at the same time in my house here, I've got clients that are 802.11n, and everybody coexists just fine together because of this mechanism. All right. So, MU-MIMO in 802.11ax. The difference is that in previous MU-MIMO modes, we were speaking a single stream of data to each one of the stations. So we've got this birthday cake looking access point that we've got in the middle here, a number of antennas, and these number of antennas all contribute to the fact that in this case I can have four in this graphic. I can have four different streams that are talking to my access points. In the case of 802.11ax now, I can have multiple streams that are going to the same client because of the way this resource scheduling mechanism and the whole business works. So what that allows me to do is it allows me to pass the same amount of data that let's say station 1 here requires. It's watching a movie, right? So there we go. So the station 1 is watching a movie. Station 1 here in an AX environment might be watching the same movie, but it's taking only half the time on the air because of the fact that that I've got now multiple streams that are actually coming to that device. So my access point is free in this other time to go service other Wi-Fi clients. This is an order of magnitude increase in efficiency compared to what 802.11ac, for example, can supply over the same in the same amount of time on the same channel width. So let's take a look at a sample 802.11ax access point. There's a couple of things here that this is Cambium's XV3 -8 Wi-Fi 6 access point. So it's a 3-radio, tri-radio, 8x8 MIMO access point with software-defined radios. This is really common. All the manufacturers that are building 802.11ax products have this type of architecture in their devices, and so. Just look at this feature list. Who ever heard of such a thing, right? So the maximum PHY rate at full signal quality, right, 1024 QAM, I can pass more than a gig of traffic over my 2.4 gig radio. I can take and pass almost 5 gigs of traffic over my 5 gig radio. These maximum PHY rates are crazy, but nevertheless. This is kind of the order of magnitude increase that the efficiencies that I've talked about in a few slides up till now enable. The radios that are included in this box, look at this. So I have a 2.4 gig radio that's capable of 802.11b, G, N, and AX. I have the ability to configure 1 8x8 or 2 4x4 radios in my 5 gigahertz radio supporting 802.11a, N, AC, and AX in one box. Gives me incredible configuration freedom to be able to make this network do whatever it is that I really need it to do. And then on top of all of that, I've got a Bluetooth low energy radio that's included in that as well. So for specific functions that I might be able to use this Bluetooth radio for in the future for other things as well. So all built into the same package because it's all part of the 802.11ax chipset. We have all of these features. So this is wireless LAN. Now let's take a look at an access system. At an access system, I'm going to pick on Cambium's EP&P Force 400 series equipment. The EP&P 4000 family, which is the access point and its related equipment, are to be released soon. But look at some of the specs that we have for this. So we got a maximum capacity of a gig at the subscriber unit. We have sensitivity that lines up with a couple of months ago. I did a little Tech Talk on Shannon's theorem. Well, this adds up exactly to that with a noise figure of less than 5 dB for those of you who understand RF. But it's as sensitive as it can be in order to get up to the modulation levels that we need to operate at, but we can. So so we've got the same system now in an access system that is being used in a wireless LAN system. That means a whole bunch of things. One is that the chipsets that are built, 802.11ax chipsets now, can be used in both wireless LAN and wireless access types of systems. And so my point for all of this 30 minutes that we've been talking here is to take and just say that this 802.11ax is going to be very pervasive. It is going to be in access systems, and it is going to, of course, be in wireless LAN systems that it already is now. And as we move on to 6 gigahertz using automatic frequency control and you know, those types of things that are scheduled for this increase in spectrum in 5 and 6 gig, we're going to see the AX protocol is going to be used in many devices, and so we're going to have this, I want to call it an increase in performance, in capacity, in increase in density, and we're just going to see this all over the place. So 802.11ax chipset will be integrated into much of unlicensed broadband equipment over the next few years. Huge range of features, and this is only getting to be more pervasive all the time. The features are only limited by imagination and what the market demands right at this moment. But there are things that this 802.11 protocol is going to do, and of course the next generation is some of the documentation talks about Wi-Fi 7 coming by 2023 or 24, something like that. So this is going to evolve then, just like LTE has evolved. This is going to evolve into something even more than that. 4x4 MIMO is going to be the minimum configuration, which is 2x2 MIMO now is probably the most popular form of MIMO. Some systems are still SISO, but not very many. Most of them are all at least 2x2 MIMO, but 8x8 and more is going to be possible using this protocol. So we're going to see more and more higher order MIMO configurations as time goes along here with 802.11ax. And of course, at the same time, better antenna technology is going to be developed to take advantage of these available features. So because the cost of the access point is coming down because of the volume that manufacturers are able to produce, we're going to be able to use smaller coverage areas, right here, smaller coverage areas, and with higher gain horn type, our antennas are going to become much more common. So we're going to be able to take advantage of this where we need the density, where we need the range. We're going to be able to take and of course use again higher gain sector antennas to reach out and maintain the same ranges that we're used to today, but at a higher performance levels because of the fact that maybe now I can put six access points up on a tower. I can use 33 or 45 degree antennas on it, and reach out my 3, 4, 5 miles, whatever it is, in unlicensed that I need to do, and be able to take and serve these customers at 256 QAM. Whereas today, with technology I have today, maybe the best I can do is 64 QAM or even 16 QAM. But we're going to see that become much more common as well. We're going to see this 30 dB SNR kind of be the new minimum of high quality links. So we're going to see systems that are going to be able to do 30 plus, and network designs are going to have to be able to reach that kind of SNR in order to make this work. And so in order to do that, again, smaller coverage areas, that's going to be the key to being able to achieve the performance and the density that we need for this. But once we have the features, once we're able to do the capacity, then we're going to be able to look at this sort of network design. And probably over the next few months, I'll have more on how to design these networks and the gotchas and that kind of thing that we have to be able to make them go. So now let's move into our next topic here is 802.11ay. So it's just coincidental that the AY protocol comes after the AX protocol, but this is we're going to see it as the protocol that's going to be most useful. It's designed to be above 45 gigahertz. So use that as the floor. So we're talking about 60 gigahertz in this particular case, unlicensed around most of the world. And so here in North America, for sure, we're going to see these 802.11ay networks begin to show up in all sorts of places. Few things about this that are important, I think. One is that we're using the controls on the physical layer and the MAC layer that we're used to, 802.11 type of controls. So, and the maximum throughput of this is definitely an order of magnitude more than anything that we've seen before. The plan for 802.11ay is to reach at least 20 gigabits per second in capacity. This is huge. This is of course monstrous, right? This is fiber-like, and so now the next step in fiber, of course, is wave division multiplex in order to but we're going to have a device now that can get hung at the end of a fiber run and extend that fiber without any compromise of capacity. And 802.11ay is going to have a role in mesh because of this capacity, and backbone networks because of the fact that now we've got a short range, very high quality system that we can use just as though we have a fiber facility that's running in between buildings or whatever the case happens to be. Lots and lots of uses of 802.11ay. So here we go. Our first incarnation of this 802.11ay protocol is in Facebook's Terragraph system. So here we are at 60 gigahertz, unlicensed operation only. That means that at 60 gigahertz, the range is going to be somewhere between 100 meters and maybe 1 kilometer, depending on the antenna types and what you're doing, that kind of thing. In this particular network, this range here typically is going to be 250 meters. This range is likely going to be about the same, but it could be a little bit more. So 250 to say 400 meters. And then if we're going to do it's possible that we could be doing point-to-points in here. And so this range, for example, this could be up to 1 kilometer, give or take. And we're using 16 up to 16 QAM in modulation level. We are using a 2 gigahertz channel, 2.016 gigahertz channel, actually, to pass this traffic. So that means that I got tons of capacity, and we're using a TDD air protocol on this thing and a mesh architecture. So what does all that mean? All that means is that the actual traffic that I have enough capacity for the traffic that I carry across this network, that I have time to manage my mesh. I have time to have an uplink and a downlink interval. I have time, because of the 60 gigahertz now, and line of sight only operation here in this. I have a very high symbol rate. I have the ability to separate my channels by polarity, by you know, a number of different methods. So typically in the 60 gigahertz band here in North America, we have 4 channels. We're capable of 4 channels. And I can take and you build a mesh network like this all on the same channel and manage it just fine. I can take and use multiple channels and of course increase the complexity of the network, or I can bond channels together as part of the standard. I can do channel bonding. And I can bring 2 channels together, and so I can take my 1.7 gigabits here per direction, which is kind of the standard for 50-50 operation and 16 QAM over a 2 gigahertz channel. I can pass a gigabit or 1.7 gigs per second of traffic. If I bond 2 channels together, this can become 3.4 and so on as we bond more channels together. Part of the standard channel bonding. And but let me talk about 60 gigahertz now as a frequency band. It is subject to oxygen absorption. Our wavelength is now short enough in 60 gigahertz that oxygen in the atmosphere provides a significant amount of attenuation, which contributes to this 250 meter channel, this range that we have. Also, rain becomes very significant, just like at you know, anything really above 20 gig. Rain is also a significant factor in attenuation over the link here, which also contributes to that 250 meters. So we most of us here are in rain zone K, and so in rain zone K, these numbers, the 250 meter number is valid. If we move to rain zones that are higher than that, we might have to be shorter. If we go to, you know, the middle of the desert, we can probably take and increase that by you know, a few 100 meters or a couple hundred meters, depending on what we want to do. But at any rate, that's the kind of architecture and system design that we're talking about here for 802.11ay. All right, talk about a few devices on here. So in almost every manufacturer's network, once you get above a certain size, you can have the controller that's built into the distribution nodes. New terminology here: distribution node and connection node. Connection node is the CPE device or the end, and the distribution node, of course, is just that, and it participates in the mesh and you know, repeats the signal from the point of presence on. So we need oftentimes as networks get to be more complicated, they need an end-to-end controller. And so the end-to-end controller is it looks after this mesh management. The latency, typical latency across this network is less than 1 millisecond, right? So we're talking about. Let me latency of less than a millisecond, and so the controller needs to work very fast. When a mesh link fails, it is established in another direction, you know, very, very quickly. So with internal the controllers that are built into the access points, generally the manufacturers are speccing, you know, 20 or so devices that is practical for that. And then an external end-to-end controller, well, there's no limit in the size of the complexity of the network that we have to be able to do that. In Cambium's case, the device agent talks to CN Maestro for management. Other manufacturers, of course, have other methods of managing the network, ranging from web management right through to command line access for configuration and control and management of the network. So let's talk a little bit about the mesh for a moment here. So there's a standard for it, and generally the meshing is based on layer 3 as opposed to layer 2. Devices or networks that are still all layer 2 are generally a tree type of or a hub and spoke type of configuration. Systems that are layer 3 based are either IP version 4 or more. As time goes along here, IP version 6 is going to become much more of a popular management mode. There's also manufacturers now that are using name management only. So you name the connection node, you name the distribution node, and then the management system will just speak to that name, and it'll resolve that name, and you'll be able to take and deal with managing the network that way. Here in this case, I have this really simple little mesh here. So I've got my 6 DNs that are connected together. The system assigns a weight to get to the POP. So it knows that the DN number 1 here is the POP, and so when I have a CN that's connected to say node 6 here that I have. Each particular route has a particular weight. It tries to enable the shortest or the smallest weight first, the shortest route from a time perspective first. So in my case here, normally the route would be 6 to 5 to 4 to 1 in order to get to the internet as quick as possible. If something were to happen to, say, that node right here, the mesh would immediately take over and reroute my traffic. So my new route would be 6 to 5 to 2 to 1. That's of course how all meshes work, but this is happening in very short time frame, and this the mesh rebuilds itself as it needs to, because of the fact that we've got all this capacity that we've got running between the access points now. I can dedicate maybe 50% of the time or 60% of the time to subscriber traffic, and the other 40% of the time I can take and use for housekeeping and mesh management. Very, very powerful. One of the reasons that mesh and Wi-Fi has failed in the past on a large scale is the fact that there isn't enough bandwidth for the subscriber traffic plus the mesh management. So here we get 802.11ay takes us past that hurdle. In the case of design of the network, I used some of Cambium's recommendations here. So each node should have at least 2 sectors connecting to other DNs in the network in order to form up this mesh. If we don't, of course, if 1 was connected to 2, connected to 3, for example, here to 6, and 5 didn't exist, say 5 didn't exist here in this particular case, then if anything happened to 2 or 3, I would lose my communication with 6. But this equipment is relatively inexpensive, and as long as I have the biggest part of designing the network is actually deciding where my DNs are going to be located. And if I do it right, I have this whole mesh arrangement here, and then I'm going to have redundancy that's built into my network in order to take and operate. More sectors I have, the more my reliability increases, and the potential bandwidth of the mesh I can take, of course, as my network gets bigger and bigger. If I wanted to feed the network over here, touch my screen, I could feed another POP into another DN on my network, and then the mesh capability of this would take then and route the traffic from one pop out to particular DNs, the other pop out to other particular DNs, and so now I've just increased the WAN capacity of my network. This is going to become, again, as we build more of these 802.11ay networks, this is going to become more and more common. And we just had a webinar this morning from a manufacturer that talks about having a GPON client into the DN, so it can come off of a traditional fiber system and extend the traditional fiber system. Features like that are going to become very common as well. All right, so let's take a look at Cambium's offering here just for a minute. They really have three devices that are on here. The V5000 is the distribution node, the client nodes, long range, high gain antenna on a V3000, and a smaller gain antenna on a 1000. Some features differ between the 3000 and the 1000, but essentially, got a list of the table of possible bandwidths that we have in between the devices here. This, of course, is full channel bandwidth, right? It's not. We haven't. It doesn't take up the fact that our TDD in this case is 50/50. So I would have 3.7 gig total when I'm at maximum modulation level on a single channel, and I divide that in half, and I get my 1.7 gigabits of capacity in each direction. So their configuration, Cambium's configuration of their distribution nodes, in this particular case, got 2 sectors built in, and these things cover 280 degrees. So it's kind of designed for the mounting pole to be right there, and then the specs are listed here. I won't go over those in too much detail, but one of the things that is absolutely true with this 802.11ay is that the access points, no matter what manufacturer we're talking about, use beamforming, and in that simplifies the business of aligning the subscriber units. Again, when we use the high gain, we're talking about a 1 degree or less than 1 degree of beam width for the subscriber unit. So we have to be quite accurate about this. But the short range means that we can, we have to be able to see the distribution node. So well, it's going to be a little bit tricky to the first few installs that you do of this kind of equipment. Once you get used to the sensitivity of the azimuths of that, it's going to become easier and easier for you. All right, so I included this with just so we can see some of the antenna gains here. So the V3000 has a couple of options: 44.5 dB or 40 dB gain antennas, and so we can use in AY the connection node for almost every manufacturer, I think, can be used as either a point-to-point or as part of the point-to-multipoint. And just a little bit about network management here. Interfaces of the equipment, point-to-point management, or standalone, or with in Cambium's case with CN Maestro manages the entire network here. And here's a system that was put up, and here's a real typical speed test. All right. So let's look at Siklu's offering for a minute here. It's a little bit different, and Siklu have their distribution node has 4 sectors instead of 2 sectors, 4 90-degree sectors. It's meant to be mounted on top of a pole, or it can be mounted behind the pole, and it'll cause a shadow in the the direction the pole's in. But nevertheless, we have 4 wide-angle sectors. We use beam steering exactly the same way, and then they have a number of different terminal units. The terminal unit, you see here, the antennas. In this particular case, the antenna is built in, and we've got a number of interfaces coming out of the subscriber unit here for both fiber and copper. And here's what a typical architecture will look like using the N366 here, distribution nodes, and bridging on the network is performed by the standard. So there's nothing on the network here that is going to be tricky or and as we go along, you make your network more complicated. It's going to be fairly easy to add to the network. Radwin also have a Terragraph offering. They again, both distribution node and client node, and some of the specs here. And Radwin have their own OSS, of course, and so management of the network is very easy. Management, adding clients, simple. Integrated beamforming antenna, 90-degree coverage. So these Radwin have taken and opted for a single sector in the antenna, and so you put up as many access points or distribution nodes, I call them right, distribution nodes, at the hub site that you need to take and provide the coverage and the performance that you want. One of the things that hasn't been mentioned so far, I guess I did just briefly, is that all of these 802.11ay networks can operate on the same channel in a mesh. And so this is the definition of frequency reuse 1. So I can take and I have 4 channels to work with in the band. I can take and let's say use channel 4, which has the lowest oxygen absorption, if I want to do that, and then put all of my distribution nodes, and of course by default the client nodes end up all on the same frequency, and we have enough time and the coverage and the limitations that enables us to be able to do this. On other networks, what stops us from using the same frequency across the whole thing, across the whole network, is the fact that our coverage areas are too big and we have too much self-interference. And of course, everyone with this 802.11ay has cool tools. So one of to make a large mesh network successful, we need to plan it. We need to plan it carefully. We need to plan our DN locations, and we need to know what clients we can connect to, and what distribution nodes a particular client can connect to. So in this case, I've got a client that's right here, let's say, and I might have the ability to connect to that distribution node or this distribution node, and my cool tools here are going to be able to tell me which one is going to be the best one to connect to, so that I can take and maintain the highest performance on my network. Most planning tools, advanced network planner that Facebook provides, as well as tools that the other manufacturers provide, generally will help us with the planning the DN locations, where we're going to need to use point-to-point links. Some tools will give us a capacity simulation when we build a network a particular way with a point of presence at a particular location. It'll tell us what the capacity across the network is going to be, and it might give a recommendation as to where we're going to need to put that point of presence. They give configuration assistance, and then depending on the manufacturer, there might be specifics about the tools that the configuration or whatever happens to be that their particular tool provides. And if we had another few hours, I probably could go into some details on some of these tools, but nevertheless, this is very necessary to make this AY network perform at its best. So I want to thank you. Can't believe our hour's up already, but I want to thank you for joining today. And if you have any feedback or want to provide any comments, please feel free to do so. Just send email to marketing@mbsiwave.com, and all of us that will see your comments. If you got suggestions for topics that you'd like me to broach, then please just send an email, and love to hear from you. And I want to thank you for your time today.
I'm sorry to interrupt.
Oh, that's all right.
My voice is echoing through your speaker. So you have one question in the chat.
Oh, okay. Can you read it to me? Where's my chat? I lost my chat on my screen.
No problem. Neil wants to know if AX will be a part of the new 6 gig band.
Yeah, that it's the reason for the 6 gig band. Absolutely. And so yes is the answer to that question. Wi-Fi 6 is definitely going to be a strong part of that. Indoor access points are indoor systems are going to have less restrictions on them, but outdoor systems are going to be allowed in the band in different segments of it, and so we can look forward to much more capacity that we're going to be able to use in situations where AX is going to be the right system. All right. If that's our question list today, then I really appreciate that, Neil. Thanks. And anyway, I wish everybody a good day, and we'll talk to you soon, I'm sure.
Thank you, Dave.